Hi everyone, I'm Yuhan. I'm a PhD student at University of Chicago. Today I'm going to present our work, ChameleonAPI, automatic and efficient customization of neural networks for ML applications. ML APIs are a popular solution to ease developers' burden in integrating machine learning solutions in their applications. Developers can write local programs with traditional programming languages, and they can invoke ML APIs with a single line of code. Then the cloud API service processes the user inputs and returns the outputs back to the local ML app. Note that this particular work does not cover large language model APIs, while only focuses on traditional APIs like traditional language API or vision APIs. Because ML APIs are very easy to use, its adoption among open source applications has increased tremendously on GitHub in recent years. In this talk, first I'll present our findings on the gap between how ML models behind ML applications are trained and how they are used in real applications. This part is backed up by our empirical study of real-world ML applications. Then I'll talk about our solution called ChameleonAPI, which uses program analysis to automatically extract how applications use ML apps, and use this summary to refine ML models with application-specific loss function. At the end, I'll tell you about how ChameleonAPI can provide great application accuracy improvement. Let's first take a look at the gap between generic ML models and the applications that use them. Generic vision models are trained to label images, and generic traditional language models are trained to label sentences or phrases. However, getting the label right is not the ultimate goal for the applications that use ML APIs. Let's take a look at this example. This app is supposed to examine a photo and decide whether the photo contains landmark, person, or building. To do so, the application first defines 3 lists of labels, and we call these 3 lists of labels 3 equivalent classes. And then it invokes the label detection API, which performs a multitask image classification. And then it compares the output labels with the equivalent classes. And to do so, it defines several if conditions. For each if condition, it goes through all the outputs returned by the label detection API. And for each label, it checks if it is in the landmark equivalent class. If so, the if condition will be evaluated to true and return landmark. Similarly, it defines other if conditions. At the end, the application will settle down to only 1 equivalent class, just like in a multi-choice question. So take this example, given a Golden Gate Bridge image, ideally, if the ML API only outputs 1 label, and that label is correct, which is landmark, the application will settle down to a correct decision, which is returning landmark easily. However, even if the ML API's output is wrong, for example, misclassifying this Golden Gate Bridge photo to be a sculpture, the application's decision could still be correct. This is because the sculpture matches the first if condition because it's in the landmark equivalent class. So the output will still be returning landmark, which is a correct decision. Here we call this list of labels equivalent classes because all the labels in the class lead to the same application decision. We can see that any misclassification within an equivalent class is non-critical to the application's decision. We wonder how large equivalent classes are in real-world applications. To figure that out, we performed an empirical study. Specifically, we created a set of 77 apps on GitHub that make control flow decisions based on ML API's output, covering 2 vision tasks and 3 NLP tasks, as shown in this table. So among the 77 apps, we found 121 equivalent classes in total. And among the 121 equivalent classes, about 3/4 of equivalent classes contain more than 1 label in it. This tells us that there can be many non-critical labeling errors in the apps. We also found that the equivalent classes are very different for different apps. So 335 labels only appear in one app, while only 46 labels appear in more than one app. Therefore, there could be a big benefit in model customization. Of course, we are not always lucky, and incorrect labels from the ML model do lead to incorrect application decisions sometimes. Take the landmark classification app again. If the output only contains lady, the application will break at the second if condition, returning person as a decision. Clearly, we can see that misclassification across equivalent classes may be critical to the application decision. Fortunately, we found that there are not many equivalent classes in each app. Unlike the generic models that need to classify more than 10K labels, the maximum number of classes the applications need to be classified into is only 7 in our benchmark. Finally, even if the output contains the correct label, it is not guaranteed that the output decision will be correct. So the ML models usually output multiple labels with the highest confidence label output first. So in this example, the model may output lady followed by landmark, which is pretty reasonable. However, in this case, when the application compares the output labels with the equivalent classes, it will break at the first if condition. This is because when it iterates through all the labels output by label detection, it finds that the second output label is in the equivalent class. That's output returning landmark, which is a wrong decision. Fundamentally, this is because the landmark apps developers give different priorities to different equivalent classes, with the landmark class the highest priority. Consequently, a low confidence label in the landmark class ruined the high confidence label from the person class. Not all applications give different priorities to different equivalent classes. For example, an application could treat all its classes equally important and instead give higher priority to ML API output that has higher confidence score by implementing the decision logic slightly differently. So in this case, if the application is written in the way that the highest confidence score output is checked first, the application decision will be different. So in real applications, we find that both types of prioritization exist. Among the 35 applications in our benchmark suite that makes multi-choice decisions, 7 out of them are like the landmark application with the equivalent classes ordered. And the remaining 28 follow the order of ML API's output confidence order. And there are more types of application decision-making among the 77 apps in the empirical study. That includes multi-choice decisions which we have seen. And there are also multi-select decisions wherein the applications can select not only one option out of all. There are also other applications make true-false decisions. So whether a specific ML model's error can lead to an incorrect solution depends on the application decision-making logic. So now that we have understand that ML model's error may or may not be critical to an application, let me now introduce our solution, ChameleonAPI. Due to the time limit, I'll only talk about it at a very high level. So we first define an abstraction called decision-making summary that reflects how applications make decisions. We have also designed a static analysis routine to automatically extract the decision-making summary from the source code using program dependency analysis and others. For example, this is what our analysis will extract for the landmark application. After that, we construct an application-specific loss function as shown in this slide. You don't need to understand the formula for now. You can find the detailed rationale in the paper. So the high-level takeaway of this loss function is that it only penalizes errors that are critical to the application. and it can be instantiated based on the application's decision-making summary. So this loss function does not penalize round labels belonging to the correct equivalent class, and it does not penalize round labels belonging to a round target class but of a lower priority than the correct target class. And however, it does penalize predicting round labels belonging to a round but a higher priority type equivalent class. And it penalizes the error set that's not predicting an label belonging to the correct equivalent class. So with this loss function, we can retrain the generic model to minimize the model errors that would be critical to the application that uses the model. Instead of using the original training data set that used to train the generic ML models, which contains images of many different irrelevant labels, we resample the training data set so that the data irrelevant to the equivalent classes are not included. This does not only save training time, but also yields higher accuracy. Now, to put everything together, the overall workflow of ChameleonAPI is shown in this figure. So at the application development phase, the developers run the parser plugin to extract a summary of how applications make decisions, and then upload the summary and the app ID to the ChameleonAPI's backend. Then the backend uses the summary to filter data and also construct the application-specific loss function and use them to retrain the model, and then save the customized model together with the app ID to the storage backend. At inference time, whenever there are requests coming in querying the same app, the application ID is sent to the backend, and the corresponding customized model will be selected, and the queries for this app will be served with that customized model. So ChameleonAPI can also be used outside the cloud service context. Developers who want to train and host their own models can use ChameleonAPI to easily customize an open source generic model to feed their application's need. Finally, let's take a look at the evaluation of ChameleonAPI. We use application accuracy as a metric. Specifically, it is a fraction of correct decisions among the testing data. We use 57 apps covering different ML tasks, including image classification, object detection, and topic classification. And we compare ChameleonAPI with 3 other schemes. So first, we compare it with a best-of-API scheme. And for this baseline, the input image is sent to 3 commercial ML APIs and takes the best out of it. This baseline is the oracle of the accuracy it will give because we assume we actually knew the ground truth label of it. We also evaluated on generic models, which are the models we start fine-tuning our ChameleonAPI on. So the generic models that are used for each ML task is listed in this table. People may wonder, is per application customization really needed? So to answer that question, we built a baseline that first specializes different models for a bunch of categories. For example, natural objects, artificial entity, etc. And then we assume that there is a magical way to determine which categorized model should be used to serve the application. For example, in this case, that natural objects model will be used to serve queries of the plant image. So this baseline serves as a middle ground of wherein like the models are customized, but not per application, but it's customized for a bunch of categories. So these are the accuracy for best-of-API, generic models, and pre-specialized models. We can see that the pre-specialized models do have better accuracy compared with the generic models. And ChameleonAPI is able to greatly improve applications accuracy from 69% of the generic model to 84%. We also evaluated how long does the ChameleonAPI's customization takes, and we can see that ChameleonAPI's customization delay is very small. To conclude this talk, we have seen that there is a gap between how ML model is trained and how they are used in applications. Then we talked about ChameleonAPI, which can automatically extract the decision-making summary of the applications and retrains the model with an application-specific loss function. At the end, we have seen that how ChameleonAPI is able to greatly improve applications accuracy from 69% to 84%. Feel free to check out our code and our paper online. And with that, I'm happy to take any questions. Thank you.